Will we ever be able to complete physics? It's pretty much the ultimate existential question for anyone who geeks out over science. Are we, as humanity, ever going to achieve a 100% complete, utterly flawless understanding of exactly how our universe operates? Or is that just fundamentally impossible? Today, we're going to dive into the biggest, most stubborn mysteries plaguing modern physics to find out. Welcome to this explainer. I want you to think of today's journey kind of like a cartographer mapping out human knowledge. We're going to visually chart the territories of what we actually know, and more importantly, we're going to sail right off to the hard edges where our understanding just stops. We are mapping the absolute limits of modern physics. So here's our map for this explainer. 1. The 8 pillars of physics. 2. The quantum gravity chasm. 3. Dark matter and energy. 4. Impossible experiments. 5. Gravitational waves. And finally, 6. Our floating cosmic museum. Let's get right into it. All right, section 1, the 8 pillars of physics. So to really understand what we're missing, we first have to define what a complete physical theory actually looks like. And basically, our universe rests on 8 distinct pillars. First up, the stage. That's 3D space and time. Next, the stuff on that stage. Matter, which is mostly atoms, and energy, which dictates how, anything happens. And finally, the forces. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Now, as you can see mapped out here, classical physics, relativity, and quantum mechanics handle different chunks of this reality perfectly fine. But here's the kicker. Absolutely no single theory we currently possess can explain all 8 at once. Which brings us to section 2, the quantum gravity chasm. And this chasm exists because our 2 absolute best theories, they just don't mix, not even a little. General relativity gives us this incredibly accurate description of space, time, and gravity, and it relies on a smooth, continuous space-time fabric. But quantum mechanics, which handles matter, energy, and the other forces, operates with this blocky, chunky, highly granular nature. When physicists try to mash these 2 sides together to create a unified theory of quantum gravity, the math just breaks. It spits out impossible paradoxes and infinities. They've literally been trying to solve this for over 100 years. And the crazy part is, without it, we simply can't understand extreme environments where both theories have to coexist, like right inside a black hole, or at the very moment of the Big Bang itself.
Let's keep exploring. Section 3, dark matter and energy.
A mere 15%. I really want that visual to sink in for a second. That tiny sliver is all the normal matter in the universe. That's stars, planets, you, me, everything described by the standard model of particle physics. The remaining 85%, completely unknown. We just call it dark matter. Now, physicists suspect we might not actually need a grand theory of quantum gravity to solve this specific puzzle. It's probably just another kind of particle that only interacts via gravity, completely ignoring the other forces. But honestly, as of right now, we are entirely in the dark about it. And then, of course, we have dark energy. See, the universe isn't just expanding. That expansion is actively accelerating. It's speeding up over time. This means there has to be some inherent outward push baked right into space itself. It could potentially be a brand new fundamental force causing this acceleration, but we simply haven't mapped it onto our models yet. Moving on to section 4, impossible experiments. Okay, so science obviously requires testable predictions, right? But theoretical fixes like string theory or loop quantum gravity currently give us 0 predictions we can actually test. We desperately need fresh data. So to find out if a quantum particle for gravity, a theoretical graviton, actually exists, we need a massive particle accelerator to generate enough energy to see it. And when I say massive, I mean we would literally need a solar system-sized accelerator. Look at the steps for this. The logistics are absolutely absurd. Step 1. Build an accelerator the size of our entire solar system. Step 2. Build a particle detector the size of the planet Jupiter. Step 3. Turn the whole thing on and, oops, accidentally create a massive black hole? Yeah. Practically speaking, this whole shebang isn't getting built anytime soon. But it perfectly illustrates the sheer, mind-bending limits of our current experimental capabilities. So let's look at an alternative that's a tiny bit more grounded. Imagine taking a massive 1-ton chunk of solid metal and cooling it down as close to absolute 0 as physically possible, just to remove all the vibrational energy. Then, you just wait. You wait for a single graviton to bump into it and make it vibrate microscopically. While that's slightly more realistic than a solar system-sized machine, it's still near impossible to physically shield a detector like this from other background vibrations like cosmic rays or neutrinos. Plus, and this is a big plus, this entire idea still assumes that gravity even uses particles in the first place. All right, let's pivot. Section 5, gravitational waves. Since we can't practically run those impossible particle experiments, we have to look for new clues by actually observing space itself. I'm talking about gravitational waves, literal ripples in the fabric of space-time. These were mathematically predicted by general relativity way back in 1915, but we didn't actually physically discover them until 2017. Currently, we can only detect them from massive cataclysmic events like black hole collisions. But looking ahead to the mid-2030s, the planned launch of the LISA space detector could be an absolute game changer. If LISA gets off the ground, it could detect primordial gravitational waves that originated from mere fractions of a second after the Big Bang. That would offer the ultimate clue we desperately need toward a working theory of quantum gravity. But guys, here is the harsh truth of our map. Even if we miraculously perfectly solve quantum gravity tomorrow, there are permanently hard edges to our universe. There are forever unknowables. We will literally never know what happens inside a black hole because no information can ever physically escape its gravity. We will never know the origins of the universe before the Big Bang because there is no surviving information to tell us. And we will never know what exists beyond the 48 billion light-year radius of our observable universe. The physics out there could be entirely different, or it could be made of antimatter. We simply cannot know.
This brings us to our final stop, Section 6, our floating cosmic museum.
Now, I know that realization might feel a bit sad or isolating at first, but instead of focusing on the cold, expansive limits of the unknowable universe, let's pivot back to our tiny, highly observable home planet. As this quote beautifully puts it, the Earth is a floating museum of the possibilities of the laws of nature. Sure, our physics may be incomplete, but out of all that cold, dark, empty space, we exist in this precious little corner where matter and energy have actually evolved and arranged themselves into something incredibly vibrant and alive. And that existential perspective is exactly why it is so profoundly heartbreaking when species go extinct. Life forms are these unique, unrepeatable configurations of the universe. When they're gone, they will never, ever exist again. This exact cosmic perspective is what drove the creator of our source material to partner with an awesome community called Planet Wild, joining over 20,000 members who are pooling their resources to actively protect Earth's biodiversity. By funding hands-on missions to save everything from pangolins facing illegal trafficking to protecting the world's incredibly unique fungi, it's just this beautiful, proactive way to cherish the anomalies of nature that we actually can interact with and understand. So, we have mapped out the massive gaps in our physics, from the mysteries of dark matter to the crushing quantum gravity of black holes. We've accepted the hard physical edges of our reality. But I want to leave you with this. If we can never know everything, isn't it absolutely incredible that we can even ask why? The very fact that this floating museum of a planet produced minds capable of looking up, visually mapping out the universe, and relentlessly testing its boundaries is a marvel all on its own. Thank you so much for joining me on this explainer. Keep asking why.